Talk about the Atiyah Floer conjecture.
Oh. So thank you very much. I think the director mentioned about this 1994 program, and unfortunately I was born that time, and also I was a mathematician already that time, so it means that I'm not so young compared to many of the participants. However, what's good is that I was actually attend that program, and that is the first program in simplex geometry, big program simplex geometry I ever attend, and it was very nice for me. So I was very happy about that, and also I'm very happy that I came back for this following conference. And the title is Atiyah Floer conjecture, and I was supposed to send this title something like 9 months before, and when I was supposed to send it, and I thought that okay, we have this some good ideas, and we still have 9 months. So let us solve the conjectures and report claims proof here in this conference. That should be the ideal place. Unfortunately, we could not do it in 9 months, so still it is a conjecture. But I think we made some progress so that I can report it. And also this is a joint work with Arikabea Daimi, and some part is also Max Lipinski. And the Atiyah Floer conjecture is something about this Hegar's splitting of the three manifold, and instanton Floer homology, which is in a gauge theory, is isomorphic to Lagrangian Floer homology, which is simplex geometry. But it will come more later. So I want to make the situation a bit more general. So let me explain what is the general case we can try to study. We consider some compact semi-simple Lie group and its universal cover, and we consider oriented and closed two manifold, and we take principal G bundle, and we also consider three manifold with boundary, whose boundary is a disjoint union of two closed Riemann surface, and we have this sigma minus and sigma plus. This is somehow input and output. And suppose we have this principal G bundle, whose restrictions is this G bundle on a sigma. Sometimes I just write sigma in place of this, putting this G bundle. Okay, so now this is the situations. And in this situation, the conjecture is something like this. Suppose we have this Riemann surface with this G bundle. We are supposed to have some category, or more technically speaking, filtered APT category. And we have a three manifold, which bounds minus of sigma minus and sigma plus. Then we have these two categories which are associated to each input and output, and we are supposed to obtain some functors, more technically filtered infinity functors. And then the third thing is that you have a M12, whose negative boundary is sigma 1 and the positive boundary is sigma 2, and M23, whose negative boundary is sigma 2 and the positive boundary is sigma 3. Then we can cook up M by gluing M12 and M3 among this sigma 2. Then the kind of gluing axiom should be the invariant of this M is a composition of this. So you have this M12 gives a infinity functor from this guy to this guy, and this guy gives a functor from this guy to this guy, and you compose it, you get a functor of this M. So that is a kind of gluing axiom of the topological field theory. And I think this kind of picture largely depends on Atiyah's axiom on topological field theory, and also Graham Siegel's formulation on conformal field theory. This is a two-dimensional case. And yeah, maybe let me draw the picture. So you have this M12 between sigma 1 and sigma 2, and M23, sigma 2 and sigma 3, and we glue them to get M. And this functor is just a composition. So that's a conjecture. And it seems likely that we can expect that this proves it does a complete generality for any compact Lie group and any bundles. So that's something. And others, yeah, and also, of course, we need to say something about how it's related to gauge theory. Let us consider the case when your three manifold has empty boundary. Then the functor you obtain something like a category associated to 1 point to a category associated to 1 point. And this is there is some way we can just regard as just a kind of chain complex. So in that case, this chain complex should be instanton Floer homology of M. So this instanton Floer homology of M is defined by Floer many years ago, like 30 years ago, and it is more than 30, right? It is something like this. It is a homology group of certain chain complex, and for this chain complex, this vector space is a free module whose basis is a gauge equivalence class of flat connections of your principal G bundle. And the boundary operator is obtained by counting the solution of anti-self-dual connections on a product of three manifold class R. And I think this is defined in some cases like SU2 or SO3 by Freya. And I think this Kronheim, Rofka, those people define it a bit more general SUN or something. I don't know, but not in complete generality. So this is something expected. And also, I need to say that how it is related to symplectic geometry. So as I say that for each Riemann surface, you are supposed to associate some category. And this category should be obtained by Lagrangian Freya theory. And the Lagrangian Freya theory in this symplectic manifold. And this symplectic manifold is a set of flat connections on this Riemann surface of this principal bundle on the Riemann surface divided by gauge group. And more specifically, we take some gauge transformation which leads to this universal cover. That's the technicality.
Sorry, Kenji.
Yeah.
Can you comment on the singularities? Are you
yeah, that's main thing. So it will come. It will come.
Okay.
No problem. So in case if you have flat connections on this, then you take in case you have a three manifold which bound on sigma, then typically this space of flat connections on the three manifold becomes an image Lagrangian submanifold of this symplectic manifold associated to Riemann surface. And this is true. Typically means that everything is transversal. And in general, we can use so-called holonomy perturbations, which goes back to Donaldson, and Freya uses it, and also Herald do this in more generality. So you can define immersed Lagrangian submanifold. So in these situations, Donaldson more explicitly gave this proposal in the year 1992. It is in a conference at University of Warwick 2 years before this 1994 special year, and that actually is the first gauge theory conference, a big gauge conference I attend. And in that conference, he proposed as follows. This is a category whose object is a Lagrangian submanifold of this space of flat connections, and its morphism is given by Lagrangian Freya homology. And important is that how this composition of the morphism goes. It is this triangle, and this triangle appeared in Paul Seidel's talk also. But this is exactly the figure drawn by Donaldson in this 1992 conference. So it is a composition. So now, in case if you have a three manifold which bound sigma, then this guy in this case is not a functor because only one boundary. It is object, and what Donaldson proposed, the first approximation of this object is this space of flat connections on them. That is an immersed Lagrangian submanifold of your symplectic manifold. Then one can expect that this axiom about composition is some kind of a generalization of Atiyah Floer conjecture. And Atiyah Floer conjecture is exactly the case when M12 and M23 is a Hunter body. So that is something people start discussing. And I say that in the 1990s, there are several activities, and many people discuss this kind of problems. And I wrote some names. I'm very sorry if something is missing, but okay, yeah. So this is people who have some working on this, and there are still some works. And kind of at some point, I was working on this, and I just go to symplectic geometry, but actually it is so much related to this problem. So now, even in this 1990s, there are several difficulties known to study this problem. The first one, which Catherine mentioned, is that the space of flat connections on a Riemann surface is in general singular. It means that typically the first case, this original case, but your Floer conjecture in the case when you have a trivial SU2 bundle, then you have a lot of reducible connections, which makes this symplectic manifold to be a singular, and it is in general very difficult to study Lagrangian Freya theory, which is based on pseudo-harmonic curve, and I think so far nobody knows how to do it. So that is the first difficulty. And the second one is the following. Suppose your symplectic manifold, your three manifold M is obtained from M1 and M2 glued on a Riemann surface. Then you have this space of representations, which should be kind of first approximation of this relative invariant. And according to the axioms, instanton Freya homology of M should be recovered from these objects Rm1 P1 and Rm2 P2. But actually there is an example that this space of flat connection is actually the same, but isomorphic, but the instant of Floer homology of M is not isomorphic. So you need some more information than just a Lagrangian submanifold. This is the second point. And the third point is actually Lagrangian Floer theory is in general rather delicate things, one of the most delicate kind of Floer theory. So that in the case when this space of there are some monotonicity which saves the situation, but in the generality when this Lagrangian submanifold is just immersed, then it depends on extra, it is not defined in general, and even if it's defined, it depends on some extra parameter. And I will come to that point later. So there are three difficulties. There might be more, but this is three, I think, is the main difficulty. And first I want to mention this second and third point. It's just a kind of, you need some extra data than this representation space. And this Floer homology is hard to define in a Lagrangian Floer theory case. This looks like rather bad things, but actually both kind of has a good answer. And I believe that's something we have been working on this 20 years on a Lagrangian Floer theory, gives us a way to answer these two questions. And this is something I have been working on this Ota Ono, and also immersed case, Akaho and Joyce gave this theory. But I will mention this point later on. So I first discussed this first point, that is a singularity of the symplectic manifold. So this means that this space of flat connections on the Riemann surface is in general singular, and there is a way to to handle this, and that is a kind of long history to describe this kind of thing, like Webersman, Lisa Jeffrey, and I think the Manuelska and Woodward gave very good contributions, and there are several people, and I don't know how much we read about this theorem 1, but yeah. So now the statement of theorem 1 is the following: even though this space is singular, there exists some compact symplectic manifold which has an action of this G tilde. It's a gauge group, finite dimensional Lie group action, which is a Hamiltonian action. And you have a normal crossing divisor D in this compact symplectic manifold. So that first of all, you take symplectic quotient of this compact symplectic manifold by this action. The symplectic quotient is this singular symplectic manifold. So it means that even if you have to work on this singular symplectic manifold, you can replace it by another finite dimensional symplectic manifold, which is smooth, so that symplectic quotient is actually your singular thing. So the natural idea, which is already mentioned by Manuel Woodward, is in place of studying Lagrangian Floer theory here, you can just study this smooth symplectic manifold and equivariant Lagrangian Floer homology. So that is one part of the story. And of course, and also, if you have this 3 manifold whose boundary is sigma, then we consider this emergence. You have this smooth, so by perturbation, this is something like a Lagrangian emergence, but a singular Lagrangian emergence. Then we consider this smooth symplectic manifold and divisor complement. Then you can kind of find, you can just replace by some similar framed type moduli space, so that this guy is a Lagrangian emergence. And what is even better is that this is a monotone Lagrangian emergence. I call it weakly because in a case this is actually embedding. This is a monotone in the usual case, and one can define Floer homology, but this is actually a weakly monotone. It means that so you have some kind of a thing like this. This is Lagrangian submanifold in X, and then this kind of disk. So monotone means that the Maslov index some C of energy. So this is a so-called Maslov index which controls the dimensions. This is the energy. It's an integration of symplectic form. And the weakly monotone means that we don't require this kind of thing for this kind of things. But if you just have this disks which lift, so that that boundary lifts to this L itself, then you have this kind of equality. So your Lagrangian submanifold, which is immersed, satisfies this weak monotone property. So that is this edit. We can just prove this kind of things. And okay. And then what I want to say that this theorem, which and also theorem 2, which I will explain next, is somehow give a definition of singular side of the constructions. So that I want to mention. So theorem 2, this is something like joint work with Alcubierre Dami, and we are now writing, but it's still not yet completed. So suppose in general we have a compact symplectic manifold and a smooth divisor. And then suppose that you have a two Lagrangian submanifold in a divisor complement. And we assume that there is a compact semi-simple group G which acts on this on everything, like symplectic manifold, divisor, and Lagrangian submanifold. It means that the divisor is a G invariant and two Lagrangian submanifold is G invariant. Then the claim is that we can define equivariant Lagrangian Floer homology on this divisor complement. So I need to mention some what this means. So in a case when you don't have a divisor and you don't have any group, then you have a kind of Lagrangian submanifold, monotone Lagrangian submanifold in compact symplectic manifold, and generalizing the Floer's original work, Yongin O defined Lagrangian Floer theory in that setting. That is something also 25 years ago. And what we do is that if you just have this divisors, but then your Lagrangian submanifold is not monotone in X, but it's monotone in X minus D. It means that if you consider the disks only away from D, you have this kind of equality, but not in general. You can still do this. And yeah, maybe I think I need to mention that I think 1 year ago I met Paul Zeidel somewhere, and I asked him a question that suppose you have only monotone divisor complement, can I do this Floer theory? Maybe you forgot it? It is in Sweden. And then because he was doing this divisor thing and Lagrangian Floer theory much, and many of the work on this case is that the divisor is a positive. It means that the divisor complement is convex, and that case is okay. But this is not convex. But then I think he closed his eyes for a minute and was thinking. They finally said that, why not? Yes. Okay. So that was very encouraging. So and, after that, I keep working, and I think now we can do it, at least in the case of smooth divisor. And but I think for the general case, we need to do this for the normal crossing divisor. That I think also works, but maybe it's safer to say it's a theorem. Yeah?
How does the Lagrangians go into the divisor, or do they stay away from it?
Lagrangian is away from divisor. It's compact. I think you can do it. Okay. So now I want to explain some idea of the proofs. And the idea of the proof of the first theorem. First theorem means that you can replace the singular symplectic manifold by smooth symplectic manifold and divisor, so that symplectic quotient is the singular one. And that is called, the main idea is use the so-called extended moduli space and non-abelian symplectic cut. So extended moduli space, I think in this context, which is kind of used by Manuel's Woodward and Jeffrey and those people study this, is a set of the all gauge equivalence class of flat connections on sigma minus 1 point. And Xi is an element of real algebra, and we assume these connections is equal to Xi d theta in a neighborhood of this point. Theta is a kind of polar coordinate, S1 directions. So you have some singularity at P0, but the singularity is by Xi. And this gauge transformation is something like which is identity at P. So this is called extended moduli spaces. And what is known is that in the case, in a neighborhood, at least in a neighborhood when Xi is 0, this carries a smooth symplectic structure, and it is a smooth symplectic manifold. And also, there is a G action, which just means that we have this framed gauge transformation. So you can just have a general gauge transformation. The difference is this G. So you have this G action, and this is a Hamiltonian G action, and actually this map which I assigned this Xi to AXi is exactly the moment map. And this G is non-compact, so you divide it by the, no, not this wide group, I'm sorry, this is G itself. You divide, I'm sorry, yeah. So G divided by G is, I think it's a maximal tori divided by group. Sorry, yeah, I'm very bad in the Lie group theory, so this is a very basic fact in the Lie group. So you have to divide by G by G, not Y group. Then you have this wild chamber. And then the construction, so the next is the symplectic cut. So let me take this picture. This is a particular case of SU3. And SU3 is rank 2. So maximal torus is 2 dimensions. And this is a wild chamber. And you take some particular particular polygons, which is invariant by Weyl group. I think this kind of thing is studied also Chris Woodworth, also maybe Mein Nenken as a kind of non-abelian symplectic cut. Then we take this the domain, which is invariant by Weyl group, and you take its inverse. I'm sorry, this is not this one. This was in a maximal tori, but it's kind of, you can just put back to G. Then you take this inverse, and this is somehow manifold with corners, but then on this codimension 1 places, you divide by S1 action, and in this codimension 2 places, you divide by T2 action, and so on. So you get some, then you get a smooth manifold, and which has a divisor, and this divisor is a kind of inverse image of the boundary of this polygon. And that is a normal crossing divisor. So you have some normal crossing divisor with some nice smooth symplectic manifold. So this is a construction which is kind of give this fast theorems. Okay. So now I want to explain something about the second theorem. So second theorem is something about the G equivariant Floer theory in a divisor complement. So there are two things we need to kind of extend compared to the usual Lagrangian Floer theory. One is how to work with equivariantly with respect to G. And if you know something about the pseudo-harmonic curve, the most difficult is transversality. As you know that the transversality and symmetry is always contradictory. To make transversal, you make it some generic things, and generic thing is never symmetric. So you have to do something. And the main idea is using these virtual things, which I don't want to spend so much time. But then the difficulty is so what use this virtual fundamental chain, you need somehow take some finite dimensional reduction of nonlinear Cauchy Riemann equations. And the main difficulty to do this finite dimensional reduction is you need to fix some coordinate of the Riemann surface you study. Nonlinear Cauchy Riemann equation is something like d bar u. D bar u. And then this is defined on some Riemann surface, in this case some disk plus some bubbles. And then the main difficulty to do this business is your Riemann surface is unstable. It means that if the Riemann surface has a small automorphism group, it is stable, then you have some natural way to kind of to take a coordinate of this Riemann surface up to some finite ambiguity. And this finite group is an automorphism group of that Riemann surface. But in a general case, you have a kind of a pair of maps and Riemann surface. And if you think together, that's called a stable map, then this together is a stable object. It means that if you take into account maps, then you have only finitely many symmetric group. But you just take this source Riemann surface, then it is unstable. Then it is difficult to take to fix coordinate. So that's the basic problem and of this finite dimensional reductions, and that affects this gauge theory and this G symmetry more, because you don't want to break any symmetry. You want to do it as canonical as possible. Then the answer is the following things. So we consider somehow complex analytic analog of the notion of Artin stack. So if you know something about the Drini-Mumford stack, it's a modular Riemann surface, and the Drini-Mumford stack is something like an orbifold. But if you include non-stable things, you cannot expect to be a Drini-Mumford stack. And in algebraic geometry, it is called Artin stack. And something we just recently realized that we can just define it in a complex analytic way. So the theorem, which is written here, is for any marked nodal curve, which is not necessarily stable. You can define some universal family of its deformations, but not in a usual case. You cannot expect so. Usual deformation theory of unstable curve is just non-Hausdorff. But if you think something called a Lie groupoid, and if you consider complex analytic category of Lie groupoid, which is something like a complex analytic analog of Artin stack, then you can do it. Okay.
Yes, one question. You should make it clear that Artin here means Michael Artin, not Emil Artin.
I think so. Artin stack is by yeah.
Emil Artin was a great mathematician too.
Yeah. I think Emil Artin is a great mathematician, but I think he's a bit too early to discover Artin stack.
I knew him too.
Yeah. Okay, so now this is the kind of main ideas. I cannot say anything so many about it, but this is some main ideas. Okay, so now I want to go to this next things. The next thing is how to work on the divisor complement. As I said, that the difficulty is compactness. So in the case of the moduli space of a pseudo-harmonic curve, you have to study some pseudo-harmonic strip which lies in the complement of the divisor, and you need to compactify it. And in a case when this D is if this complement is convex, then everything is very similar in the compact case. You don't have to worry about it. But since this D is, we don't assume any convexity assumption on D, so we need to be careful how to compactify it. And there is a notion of stable map compactifications, which is kind of studied by various people. And this stable map compactification does not seem to do the job in this generality. So we need to use some another compactifications. So that is this kind of thing. So just create the statement. Suppose you have a compact Symplectic manifold with smooth divisor, and your Lagrangian submanifold is in the complement of this divisor. Then this is a moduli space which I will soon explain. This moduli space has the compactifications. This RGW means relative Gromov-Witten, some particular compactifications. And the beta is a kind of homology class in the complement. And what is nice is that the boundary of this moduli space, of this compactification, is described by this another K prime, beta prime. But its beta prime is also a homology class of X minus D. And this last property is very important. If you take stable map compactifications, then you can do a very similar thing, but this property does not hold. So if you want to use only the disks which is away from the divisor, you need to do some different, you need to use some different compactifications, not stable map compactifications. And that is this theorem. So I just mentioned a bit more. So this is MK plus 1 beta is some basic moduli space which you use to define Lagrangian Floer theory. And so I just want to consider one L. Actually, we need to consider the case of 2L, but it's not so different. So you consider this moduli space. It's a kind of disk with marked points which lies on the boundary, something like this, and the cyclic ordering. And you have this U, which is a holomorphic disk which bound on L, and its homology class is beta. So let me remind again that this beta is a homology class which lies outside of D. So you have a relative H2, but the relative H2 on X minus D. So we want to compactify these moduli spaces. And then the way to compactify is something like this. So this compactification is actually so much related to this so-called relative Gromov-Witten theory. And I think people in the relative Gromov-Witten theory study the case when you have a closed Riemann surface on a divisor complement and try to compactify the moduli space. That I think a lot of people working on it. But we want to use disks. But it seems that as far as the Lagrangian submanifold is compact, there is not a big difference. We can just do very similar business as they do. So there are many people working on it. I think what the version we are working on is very similar to this what John Lee did in algebraic category. But there are work by Gross-Zibet and Brett Parker in a normal crossing case. And also there are symplectic sites. There are Reed 1, Ionel Parker, and maybe Alexis Zinger and several people. And the main thing, I'm sorry I don't define this so much precisely, but the main thing is like this picture. You have some disks which is away from the D, and you include something which is kind of in a neighborhood of D, but you take this many blow up. And this picture, if you know something about so-called symplectic field theory, looks very much like the picture appearing in the symplectic field theory. But in the case of symplectic field theory, people study the case again convex. And also that another difference is symplectic field theory. So in our case, we consider X minus D. And the end of X minus D has a sister action. And R action means use this normal direction. And S1 action, which is related to this, the case that this normal bundle is a complex line bundle. And in symplectic field theory, people study the case when the end is something like a compact manifold cross R. So they have a R action, but do not have a S1 action. And so there are two differences. One is complexity, and the other is just symmetry. And then other than that, I think our construction of this compactification is very much similar and take a similar way as the symplectic field theory. And compactness, we can try to use, we have some good situation because we have some compact X and everything is there. And S1 actions, and the effect of this S1 action is if you know about symplectic field theory, then somehow the harmonic curve which escape to this infinity gives codimension 1 boundary. in a symplectic field theory. But in our situation, we have this extra S1 symmetry. There it is a codimension 2 boundary. It means that once we get some natural compactifications, actually you can forget it. All the boundary is just so you can just study this in the same way as a case of Lagrangian submanifold in compact symplectic manifold. So I mean, of course we have to work hard to write down the precise compactifications and to have a natural structure. But once we do it, everything looks similar to this compact Lagrangian submanifold. So that is this idea. Okay, so now that is the two theorems I just mentioned. So what it implies. So let me go back to the original case of Atiyah Floer conjecture. So Atiyah Floer conjecture is the following. Oh, I'm sorry. So original case, you have these two, Hg1 and Hd2. They are handle body of genus G, and they are glued on this Riemann surface to get closed three manifold. And then what is Atiyah Floer conjecture says that this instanton Floer homology of M is isomorphic to some Lagrangian Floer theory. And as I said, that the difficulty is that in our situations where this Lagrangian submanifold is singular, this right-hand side is actually not well defined. So Atiyah Floer conjecture is, I think, 30-year-old conjecture, but actually it was never a rigorous mass conjecture because the right-hand side was never defined. And what I believe that what we can do is just we replace this ill-defined thing by the following things. We consider this Xi of chi sigma G. That is some smooth symplectic manifold, so that symplectic quotient is your.
Should there be a group action there?
Yes. Yeah, everything is G equivariant. So you have this chi of sigma G and its divisors, and then your Lagrangian submanifold has somehow lift so that they are monotone in this complement. This is not weakly monotone because in the case of handle body, this is actually embedding. So you have a kind of embedded monotone Lagrangian submanifold in non-compact symplectic manifold, but it's a divisor complement. And this divisor complement, they are somehow monotone. And then if you use all this rather heavy machinery of equivariant and relative version of Lagrangian Floer theory, then you can define this right-hand side. I'm sorry, I forgot G. I'm sorry, I forgot G here. Yeah. Then we can expect that this closed, the right-hand side is this guy. Then I believe that this is a rigorous way to at least state Atiyah Floer conjecture in the case of handle body.
C here is SU2, right?
Yes, SU2, yes. The reason that we need to make SU2 is that actually left-hand side is not defined in that in general. Left-hand side is defined in SU2 or some SO3 cases, but this version, somehow original version is SU2, and you go further, then kind of you have some difficulty. I need to say a bit about the kind of, if you just, this guy has a reducible connections, and to make this actually a honest isomorphism, we need to choose a bit carefully how to handle trivial connection or things like that, but that's a bit technical. Okay, so now this is the first half of my talk. Any questions up to now?
Well, in the original setup, M would be a homology three-sphere.
Yes, that we need, yes.
Relevant to the right-hand side?
Yes. Yes, so it depends how we use this reducible connections. On the original case, there only are trivial connections. On the right-hand side, intersection has only trivial things. You can just throw away both of them. Then it's kind of construction parallel. And if you define this equivariant version on the left-hand side, probably you don't need it.
But the right-hand side will be defined without that assumption.
That's right.
So
yeah.
It could be a candidate for.
Yes. Actually, so the right-hand side should be defined in complete generality, any G and any something. So it's a candidate of this. This.
Whether it's stable with respect to changing the Hegel splitting.
That's right. There are several people who actually, I think Manuel Woodward already proved this kind of things in their particular setting with not equivariant versions. So I hope that we can use that kind of argument to prove it's well defined. But that's not done. So this is about difficulty 1. I just want to add up, so I not go to this 2 and 3 points. So this is, let me record that you have this 3 manifold decomposed to 2 union of 3 manifold glued along sigma. And then the problem is that the space of representation do not contain enough informations. And the other thing is that Lagrangian Freya theory is a rather delicate issue to define. But then what we have done in this is the following things. So Lagrangian Freya theory is defined in the general case if the Lagrangian submanifold has a objects which we call bounding cochain. And this Lagrangian Freya theory actually depends on the choice of bounding cochain. So this looks like a two negative statement. If you want to define invariant, then it is not always defined and it depends on the extra parameter. But if you look these 2 points, this is rather nice because this bounding cochain is actually missing information here. So as I say that Lagrangian submanifold alone is not strong enough to recover all the Freya homology of closed C manifold, but if you use this bounding cochain, that gives extra information you need. So that is this idea, and this is the kind of Agaho-Joyce to the immersed case. So let me explain why this some points about the Lagrangian Freya theory. So I think many of you know the proof by Freya's proof of this boundary square is 0 in Lagrangian Freya theory, and it is by this picture. So you consider something like a moduli of holomorphic disks which bounds L1 and L2. And you want to study what is the boundary of this moduli space, and it is drawn in this picture. And since this is a boundary of some moduli space, it is 0 in homology. That's one thing. And the other is that if you recall the definition of boundary, this configuration just calculate boundary square. So this is the Freya's original idea how to define this Lagrangian Freya theory, and Young and Go found that it works at least in a monotone case. So that is this boundary square is 0. So what's wrong about the general case? So suppose that we have only monotone Lagrangian submanifold, and it is a weakly monotone. So it means that for some disk like this, which is called a teardrop, you don't have any control about the dimensions. Then in that case, you have to worry about different kinds of phenomenon at the end of your moduli space. You have some holomorphic disk, but you have a kind of self-intersection point. There in the self-intersection point, there are some bubble happens. And this is an extra end. So as I said, that if you just consider this end gives a boundary square, and this is the end of something, it is 0. But in our immersed situations, you have another end which is drawn in this configuration. So because of this, if you try to prove boundary square is 0 in a weakly monotone immersed case, you fail. So you don't get correct answer. So the Freya's boundary operator square is not 0. So that is a kind of problem about this. And then the answer to us and Agaho-Joyce is the following. So this is a boundary operator we count. So you have a P and Q, you have like 1, L2, and you consider this strip like this. And then using this, we define this boundary P is equal boundary P and its coefficient in Q. But then something we do is that we also count this kind of moduli spaces. So this yellow one is a holomorphic disk, and you see that you have a kind of self-intersection. So you have several self-intersections on a L1 side and L2 side. You also consider this kind of many polygons as a boundary operator P and Q. But of course, we need some weight. So you have each of these self-intersections, you fix some number. And this weight is exactly the bounding cochain in this case. So this bounding cochain is something to describe which weight you count for these polygons. So you don't only count this bigon, but you have also polygon using this weight which we assign to each of the self-intersection points. So that is a kind of a boundary operator of immersed Freya theory. So let me repeat. For the definition of boundary operator of Freya homology, we will count this kind of configurations together with weight put at each of the intersection points. I mean, just multiply all the weight. And in our situation of weakly monotone, the bounding cochain is just the data which determine this weight, how you put the weight of these configurations in our case. And of course, you just choose your weight randomly. The boundary square 0 you cannot expect. But you can just write down the property of this weight so that it is necessary so that the boundary square is 0. And that is exactly something called the Molar-Cartan equations. It's very natural. Boundary square is 0 is something similar to flat connections. And the Molar-Cartan equation exactly the sum connection is flat. So you have this Molar-Cartan equations. And then if you use this bounding cochain which satisfies this Molar-Cartan equations, then in this corrected form, you can still recover boundary square is 0. So you get a Lagrange Flare theory in an immersed weakly monotone case. But you need to use this bounding cochain, and the Flare homology depends on the choice of bounding cochain. Of course, in general, what's not so good is that in general, bounding cochain may or may not exist. So if you have just a weakly monotone or immersed Lagrange submanifold, then you want to define Lagrange Flare theory, but there are cases that there is no bounding cochain. In that case, there is no way to get the Flare homology. And also, Flare homology depends on the choice of bounding cochain. So it is more natural to write it a kind of Flare homology between pair and L1b1 and L2b2. So that is this kind of something like we learned about Lagrange Flare theory in these 20 years. Okay, so now let us go back to the situation of gauge theory. Then the theorem is the following. So we consider the situation that is so first of all, kind of in a generality, we have to connect this story to the story for the part 1. It means that we have to work in a divisor complement in an equivariant way. There are some problems. So I just want to state in the case when this space of representation has no singularity. That is kind of most important case is SO3 connection with non-trivial bundles. And in that case, so we have this smooth Symplectic manifold, and then you have M whose boundary is sigma. Then this space of flat connections on M is an immersed Lagrange submanifold of this space of flat connections. So in this case, they both are smooth. Then the first theorem says that there is a bounding cochain of this particular immersed Lagrange submanifold, and it is canonical. So it means that it depends only on four manifold up to some equivalence. So this equivalence is somehow non-trivial because, as I say, that just you have a Lagrange submanifold, then you may not have an immersed. But in this particular case of gauge theory, we can prove the existence. So that is the theorem 4. And the theorem 5 is the following. If this, so this is a kind of something, some announcement under the detail to be written, and we are kind of writing some one by one by this, like the Daimi and Max Lipiansky. So suppose you have a boundary is sigma and boundary M2 is sigma, and still we consider the case this is has no singularity. Then this is suppose for simplicity this is a immersed Lagrange submanifold. Then we can use this bounding cochain to cook up this Lagrangian Flare theory, and the claim is that this Lagrangian Flare theory is isomorphic to this instanton Flare homology. So what it means that this is some kind of Atiyah Floer conjecture in a situation that the Symplectic manifold involved is actually smooth. And what is the kind of extra thing is that you can use this. I'm sorry, this is BM1 and this is BM2. Using this bounding cochains, you have this isomorphism. So that is Lagrange Flare theory. And yeah, and also in the case of the like a handle body, this is actually embedded. Then you don't need any bounding cochain. So this is kind of close to original case. So this is two theorems. So this means that, as I said, that you have this instanton Flare homology or closed thing, then it is isomorphic to the Lagrange Flare theory together with this bounding cochain. Okay. So now I want to mention the idea, basic idea how these kind of things are coming. So the idea is the following. So as I said that in our category, we consider category whose object is something like a Lagrangian submanifold. But then if you have a three manifold which bounds in your surface, then you can just think this three manifold as a kind of object of this category. So Lagrangian submanifold and three manifold plays very similar role in case of the boundary of the three manifold is sigma. So let us regard sigma as an object of this category which is associated to sigma. Then we want to find some B of M so that this object, so R of M is a Lagrangian submanifold. So R of M together with this bounding cochain is isomorphic to this three manifold as an object of L of sigma. So let me remind you, L of sigma is a category. Originally, its object is a Lagrangian submanifold, maybe plus bounding cochain. Your three manifold looks something similar to this to an object. So I want to find that this M is isomorphic to this pair. Then you can prove this theorem. So that's a kind of way we consider. I mean, from this you can think this, because this is a kind of a morphism of this between M1 and M2, and this is another kind of morphism. So if you can find somehow M is isomorphic to this pair of objects, then you will be done. So that's the idea. So now, what we want to do is that we want to find some Bm so that your 3 manifold is isomorphic to this space of flat connection together with this bounding cochain. So you want to find isomorphism between 2 objects in your category. So you want to find an isomorphism. So it means that you have a, you want to prove something is isomorphic, so you want to find isomorphism between them. So you have a category and you have 2 objects, and you want to find an isomorphism. So what is a morphism between this guy and this guy? So let me consider a bit more general. Suppose you have a Lagrangian submanifold L. It's a Lagrangian submanifold, and you have a M. So M is a 3 manifold which bounds sigma. Then I want to consider what is the morphism between this 3 manifold and this Lagrangian submanifold. It is kind of a bit more extended thing, so you have to think what is the morphism. And actually, there is an answer. It is a Floer homology of M with coefficient L. So what it is? So HFML is a instant Floer homology of 3 manifold M with boundary and using the coefficient L as a coefficient. And this kind of ideas, I think I just wrote somehow in 1992, but I couldn't do it for a long time. And this Dietmar Salomon and Catherine Wilhelm realized this kind of things around the year of 2000 or something. So that is their version of this Lagrangian 3 manifold with boundary and Lagrangian boundary conditions. So that is this things. So what is this instant Floer homology with Lagrangian boundary conditions? It is a homology of some chain complex, and the CFML has a basis which is identified with this space of flat connections and this L, so this intersection. So, and the boundary operator is defined by certain anti-self-dual equations on M cross R, and we put some boundary conditions using this Lagrangian submanifold L. So you consider some boundary value problem of ASD connections to cook up this invariant. I will go back to this a bit more later. So now, let us consider the case. So the basis of this chain complex is this intersection point. But in our case, this L is this space of flat connection itself. So that's a kind of special case of our story. Now, L is not just a general object, but a space of flat connection itself. So now, what is this? I'm sorry. Now, now in that case, these intersections Rm and Rm is Rm itself. So you are not in a transversal situation. You are something like a bottomless situation. You have just the same Lagrangian submanifold. Its intersection is this chain complex which generates this Floer homology. And then in this case, I think in a bottomless case, kind of intersection point, we replace this homology group. So this chain complex is actually a homology group of the space of flat connections. Actually, with the fiber product itself in the case in mask. But anyway, it's something like this. And then we want to find isomorphism between M and this Lagrangian submanifold. It's something like an element of the homology group. Then if you think so, that is a good answer. The isomorphism should be fundamental class. So that is the answer. And the way we find B of M is so that this fundamental class is actually a cycle. And there is some homological algebra lemma that you can find uniquely bounding cochain so that fundamental class becomes a cycle. So that is the way you obtain this B of M. And then you can use this fundamental class so that to get this isomorphism. So that is the idea. And actually, this kind of things appeared in this Yankee Rikiri and Max Lipinski's paper, which is a bit different, but in a kind of Lagrangian correspondence cases. And I think Lipinski also had this kind of idea already in 2010 or something. And then we can just use these ideas to make this work using this bounding cochain business and blah, 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 blah. So that is this story. So now, what remains to construct is a moduli space of anti-self-dual equations on M cross R with boundary condition L, and L is a Lagrangian submanifold of a space of flat connections on sigma. And we want to cook up some good moduli spaces so that we can work out this Floer homology or this L boundaries. And actually, to cook up these moduli spaces, at least at this stage, there are 3 methods which are related but slightly different known. I proposed some method using degenerate Riemannian metric in I think 1998 or something, published in GAFFA. And Salomon and Wilhelm used another method to cook up these moduli spaces in their series of papers, like Geometry and Topology 12. And Max Lipiansky proposed some other version called the mixed equations around 2010, and it is in the archive. So there are 3 different ways to do this. And what's nice in this Salomon-Wilhelm's way is that they already finished the 4 set, Fredholm theory, compactness, and removal singularity. But one drawback is that I want to make this correspondence from L to this Frey homology is a kind of functorial. It means that when you have different L's, and this correspondence should define some infinity functors. For this, their method has some problem because one need to glue ASD connections and holomorphic disk which bounds on L. And I try to do these gluings. Probably your version has some trouble to do that. So I think, but we don't need this kind of functoriality in a case when L is embedded. So that's the case. But if you want to make this functorial, I think these other 2 versions are a bit better. Unfortunately, those 2 versions there are removable singularity and compactness is written and proved, but Fredholm theory is not yet written, and we are now writing this Fredholm theory with Alexander Daimi and Max Lipiansky. Okay. So now, let me explain what is mixed moduli space, that is Lipiansky's version, which we plan to use. So we consider this 3 manifold M. I'm sorry, it's a bit small, but we consider this 3 manifold M whose boundary is sigma. Then you take this M cross R, and in this case you have sigma is a kind of finite distance. Then up to here you take these equations A with this anti-self-dual equations. But then on this part, which is a kind of interval cross R, we don't consider ASD equations, but you have a map. You have a map U from to this R of sigma, space of flat connections. Then we assume that this is a holomorphic curve. So you have a kind of equations which is a ASD equation here and a holomorphic curve equation here, and you have two boundary conditions. One is here. Here is just this, but this map is supposed to arrive in this Lagrange submanifold L. And on this line, which is called a switching line, the assumption is that if you restrict A to this point, you have a flat connections, and you take its gauge equivalence class, then the value of U coincides with this gauge equivalence class. So you have these two objects. One is ASD connection, the other is a holomorphic curve, and you assume some matching conditions on this borderline. That's what this Lipiansky proposed. And he wrote a paper about compactness and removable singularity. The version I wrote is kind of related but slightly different. I don't want to explain it now. So the main thing is that we want to prove this has a kind of natural removable singularity and compactness. And you can see that most of the things are kind of parallel to either gauge theory or pseudo-holomorphic curve. And what is really different is on this line. You have this line, so that left you have this ASD connections, right you have holomorphic curve. So if you want to prove some analysis like removable singularity or some bubble here, then you cannot rely Uhlenbeck or Gromov. You have to do something yourself. And I think what is Lipiansky proved is that he can prove this removable singularity and compactness at this borderline cases. Okay, so now that is this moduli space, and we are now working on this Fredholm theory. It seems that the Fredholm theory is very similar to what this Catherine Wilhelm did in her versions. So we can just try to use her work to adapt her work in our situations. Okay. So now, finally, so far, we have been considering the case the space of flat connections is non-singular. But let us try to consider the case when the space of representation is singular. As you see that in the first part, I just explained how to handle it in a symplectic side. We use some extended moduli space and take symplectic cut. We have a compact symplectic manifold with normal crossing divisor. And then if you consider everything in a divisor complement in an equivariant way, you get Lagrange Freya theory. So you want to match this Lagrangian flare theory to something in the gauge theory. Then you can try to do somehow similar moduli spaces like this mixed moduli spaces. In that situation, you have this singular Symplectic manifold. And then, unfortunately, what I proved in this 1998 in the Gaffer paper and Rick Jansky proved in this 2010, that we both use this the fact that there is no reducible on R of M sigma. There are some analytic points which one needs. So that's a point. That's a kind of missing ring. So if you can prove this similar moduli space as this Lipinski's mixed moduli space, you can prove this Lemberg singularity and the compactness and also Fredholm theory in its generality. Then I believe that the conjecture I just wrote at the beginning should be proved in complete generality. But that's still missing. Okay, so now the summary of the present status. We can consider 2 plus 3 dimensional topological field theory using Lagrangian flare theory only in complete generality, arbitrarily compact semi-simple structure group, including the case of moduli of flat connections have singularity. And in the case when the space of flat connections has no singularity, we can prove the symplectic story in 1 coincides with gauge theory story. And this is 1 and 2, some positive side. And I believe that we can do this, but we need a huge amount of writings to fix all the details of this full story. Actually, somehow several hundreds of pages, so hopefully not 1,000. But so that's something we need for this 1 and 2. And something really missing is 3. In case when the space of flat connection has singularity, what is missing is the construction of a Lipinski's mixed moduli space with appropriate property in that generality. That I don't know how to do it yet. That's why I don't claim it as a theorem, but it's a conjecture. Okay, so I stop here. Thank you very much.
I don't think we have all many physicists here. I don't think is Witten here. No. So no. Okay. So I asked the question that he would have asked. It's the following really. You're very much concerned with Riemann surfaces and points, and you have the group SU2. A physicist would say that's electroweak theory. But you haven't got to SU3, which is strong interactions, and SU3 involves quaternions. So you have to replace the disk and points. You have to replace it by four-dimensional space with quaternions, and then you will of course get much more deeper theory. We will have more difficulties because quaternions are of course themselves not commutative, and the quaternions contain 2 copies of the complex numbers, which will be related to your twofold. When you have a function where you take 2 copies, those 2 copies can be thought of as 1 copy of the complex numbers and its complex conjugate inside the quaternions. I think until you get to that one, and then when you do that, probably many of these problems become easier because you do it in more natural context. So I leave it as an exercise for the young people. Do this, replace the complex numbers by the quaternions.
So I have some idea how to go this another compact group, but I don't know how to include quaternions. So yeah.
You can't go much beyond the quaternions.
Should that be 1 plus 3 dimensional?
So yeah, I think there are several ideas to include knot or links in this theory somehow. But I don't know so much about it. But maybe knot flare homology, that kind of thing should be include 1, 2, 3.
Or would that but conjecturally include invariance of 4 manifolds?
Yeah, that should be kind of possible. You have a kind of 4 manifold, you have this 3 manifold, and 2 manifold cross R. You have some several more handles. Then this should give some natural transformations between functions. So that one can do, yes.
It's a bit like the Allsvall-Szabo and
yes.
building up from 2 dimensions.
Yes. Yeah. So I think one can try to do similar thing in Simon-Witten theory, but it's another analytic problem, I think. Yeah.
So, coming from more general field theory, I mean, the reason, honestly, I've stepped away from my version of this theory is the problem with disjoint unions, right? So when you try to work with a non-trivial bundle, it's like putting a marked point, and if you have a disjoint union of surfaces, it's only on one of them, and so then you get singularities again. And so I wonder, have you thought about what your resolution does when you have a disjoint?
Yeah. So what you can do is, one point you have this trivial bundle, 1 point non-trivial bundle, you can just take this mixed moduli space. No, we can take this. Extended moduli space, both of them. Then of course this one of them is originally smooth, but you can still do this, and we can prove that Lagrange Flare theory of this extended moduli space with divisor complement is isomorphic to the symplectic quotient. In a case symplectic quotient is smooth, it's a kind of relation between symplectic quotient and how this Lagrange Flare theory is going, and that is a kind of story which is, for example, people like Tian and Xu is studying, and we have some other ideas to do that kind of thing. So you don't.
Let me clarify. So my question is your extended moduli space. How, if I apply that construction to a disjoint, to a Riemann surface that's a disjoint union
Yes.
of sigma 1 and sigma 2,
Yes.
right? Then I have sort of three extended moduli spaces, right? One for the disjoint union, one for sigma 1, and one for sigma 2.
Mm-hmm.
Right, and field theory would require the category applied of the disjoint union to be some kind of tensor product.
Yes. Yes.
Is that what you expect to see?
Yes, that we can. Yeah, it's not actually so much difficult, I think.
Are you saying the symplectic manifolds?
Yeah. I think you can
product?
disjoint union, the space of flat connection is just a direct product.
So you're putting punctures on.
Yeah. And actually, we put puncture on each connected component in that case. Yes.
Okay, if there's no more questions, first let's thank Kenji again.